Petroleum or crude oil is a complex, naturally occurring liquid mixture containing mostly of hydrocarbons, but containing also some compounds of oxygen, nitrogen and sulfur. It is often referred to as the black gold. After World War II, the huge oil reserves in the Middle East became available at a very low cost, and they rapidly revolutionized the way we live. Indeed, the 20th century, with all the dramatic changes that it has brought to the society, is probably the best characterized as the century of oil. Now next, coming to petroleum formation. Petroleum forms by the breaking down of large molecules of fats, oils and waxes that contributed to the formation of kerosene. This process began millions of years ago when small marine organisms abounded in the seas. As the marine life died, it settled at the sea bottom and became buried in layers of clay, silt and sand. The gradual decay by the effect of heat and pressure resulted in the formation of hundreds of compounds. Because petroleum is a fluid, it is able to migrate through the earth as it forms. To form large economically recoverable amounts of oil underground, two things are needed. First is an oil pool and then an oil trap. An oil pool, which is the underground reservoir of oil, may literally be a pool, or it could be droplets of oil collected in a highly porous rock such as sandstone. An oil trap is a non-porous rock formation that holds the oil pool in place. Obviously, in order to stay in the ground, the fluids, that is oil and associated gas, must be trapped so that they cannot flow to the surface of the earth. The hydrocarbons accumulate in reservoir rock, the porous sandstone or limestone. The reservoir rock must have a covering of an impervious rock that will not allow the passage of the hydrocarbon fluids to the surface. The impervious rock covering the reservoir rocks is called a cap rock. Oil traps consist of hydrocarbon fluids held in porous rock covered by a cap rock. A hot, wet climate fosters the growth of large amounts of organisms. If this growth takes place in a shallow sea, the eventual drying out of the environment and evaporation of the seawater leaves behind large deposits of salt. Salt makes an excellent cap rock for a reservoir. If these conditions are enhanced by a gentle geological folding of the subsurface rocks, the rock folding can produce very large reservoirs with the impervious salt deposits acting as a cap. These are precisely the conditions that prevailed in the Middle East, giving rise to the enormous deposits of oil found in that region of the world. The elemental composition of petroleum is much less variable than that of coal. That is, it consists of 83 to 87% carbon, 11 to 16% hydrogen, 0 to 4% of oxygen plus nitrogen and 0 to 4% sulfur. Please note that most crude oils contain substantially more hydrogen than coals. Most of the compounds in petroleum contain from 5 to about 20 carbon atoms. Many of them consist of straight chains of carbon atoms surrounded by hydrogen atoms. Another class of molecules found in petroleum are the aromatic compounds. They have a ring structure and are typically derivatives of a compound called benzene, having the formula C6H6. They do indeed have a characteristic aroma, but they typically have a negative environmental impact. The ones that have a low molecular weight are volatile. For example, they easily evaporate from gasoline at filling stations. Many among them are known to be carcinogenic. As the oil is buried more deeply inside the Earth's crust, it is exposed to higher temperatures. As a result, the molecules can break apart to a greater extent, and some of the molecules containing sulfur will be destroyed. These young deep crudes will have moderate viscosities, densities and sulfur contents. If the oil has not been buried very deeply, it will not experience the same temperatures as a young deep crude. However, over very long time periods, the same chemical transformations that occur in a short time at high temperatures can also occur at relatively low temperatures. Thus, an old shallow oil might have the same properties as a young deep one. If a crude oil is buried deeply and for a long time, extensive breaking apart of the carbon chains can occur. At the same time, most of the sulfur compounds in the oil are broken down. Therefore, an old deep crude oil has low viscosity, low density and very low sulfur content. This combination of properties makes the old deep crudes the most desirable. They require little refining to remove sulfur, and they can be converted to large quantities of high quality products such as gasoline. Unfortunately, less than 5% of the world's remaining petroleum reserves are of this quality. Some of the best quality crude oils are found in northwestern Pennsylvania, in the vicinity of Bradford, and the term Pennsylvania crude is used as a standard of quality for crude oils. Overseas, old deep crudes occur in Morocco as well. Next, coming to petroleum utilization. The preparation of petroleum before it is sold to the consumers is very extensive. The reason for this is that despite their similar elemental composition, the chemical structure of different crude oils may be very different as discussed above. Furthermore, a large number of different products is obtained from the petroleum refinery. Most of them are used as fuels. A small but very important fraction is used as the basis for the petrochemical industry, which gives us such indispensable products such as plastics, pharmaceuticals and textiles. When crude oil is pumped from the ground, it may contain several hundred individual components which range from liquids of very low boiling points to solid waxes. Crude oil could be used as a boiler fuel to make steam for process heating or electric power generation, but it is only marginally more desirable than coal because of the convenience of handling liquids rather than solids. No other device can make efficient use of a substance having such a complex mixture of components. The approach to making the best use of petroleum is first to separate it into small groups of compounds. This is done in a petroleum refinery. In principle, it is possible to separate each component of petroleum one by one, though this might take many repetitive distillation operations. The key step in refining is distillation. Distillation is the separation of materials based on differences in the volatility, as indicated by their boiling points. This operation is carried out in a distillation tower or a column. At any given location in the column, there is a mixture of vapors corresponding to a liquid of particular composition and volatility. These vapors can be withdrawn from the column and condensed to form a liquid product. Such a liquid is still a mixture of many components, but in this case the components have fairly similar boiling points. The separation of crude oil by distillation is a physical process based on the fact that different chemical compounds have different boiling points. For example, pentane, that is C5H12, boils at 36 degrees centigrade, while nonane, that is C9H20, boils at 128 degrees centigrade. Because the separation is based only on a physical process, that is boiling, no chemical bonds are broken during distillation and no chemical reactions take place at this stage. Now next, coming to petroleum products. 5 broad categories of products are obtained by distillation of crude oil. Gases are mainly propane, that is C3H8, and butane, that is C4H10, that were dissolved in the oil. They can be liquefied and sold as the useful fuel LPG, which is liquefied petroleum gas. Gasoline produced by distillation of crude oil is called straight run gasoline. Now coming to the principal energy related uses of the products of petroleum refining. First is that gases are used in industries and homes as fuel. Gasoline fuel is used in spark ignition engines. Diesel fuel is majorly used in compression ignition engines. Jet fuel or kerosene is used as fuel for jet engines and gas turbines. Fuel oils are used in industrial or residential fuels. In the world of fossil fuels, natural gas is often the overlooked ugly duckling. It gets lumped in with oil as in oil and gas industry, even though the discussion usually centers upon oil. It does not help that gasoline, which is derived from oil, is shortened to gas. In many people's mind, the gas in oil and gas refers to gasoline and not natural gas. However, natural gas has much to offer as an energy source that makes it preferable to other forms of fossil fuels. It burns much cleaner than coal or oil, and it produces far less carbon dioxide for each unit of energy. Its simple chemical nature makes it a much better source to use in high efficiency fuel cells than either coal or gas. As a usable energy source, natural gas really has only one stumbling block, but it is a major one, that is, it is hard to transport and store. If the transport or storage system is not completely sealed, natural gas will leak. Further, both systems must be able to withstand high pressures in order to compact the natural gas into a reasonable space. Now next, moving on to the usage of natural gas. Over the last century, the use of natural gas has become more diversified. In 2002, 22.6 trillion cubic feet of natural gas were used in the US. Natural gas has come a long way from being used primarily to provide lighting. The greatest use today is in the industrial sector as an energy source and as a chemical feedstock for such things as fertilizers. The second greatest use is for generating electricity. This is a growing sector as the creation of new turbine generators that burn the gas in an engine and then use the exhaust to boil water results in power plant efficiencies of 50 to 60%. Most of the remaining natural gas is used for heating, hot water and cooking in homes and companies. A very small portion of the total amount is used in cars and trucks as an alternative fuel to gasoline. This usage results in reduced emissions from automobiles. Now coming to the creation. Natural gas is composed primarily of methane, that is CH4. It does contain other chemical species such as butane and propane. If the mixture is comprised only of these species, it is called dry natural gas, as there will be no liquid components at standard pressure and temperature. There might also be some other organic components such as pentanes that are mixed in with these species. These heavier species are normally liquid at standard temperature and pressure and comprise what is called natural gas liquids. Natural gas might also be mixed in with non-hydrocarbon compounds such as water vapor, carbon dioxide and hydrogen sulfide. If so, it forms what is called wet natural gas and requires some processing before it can be used. Natural gas comes from the decomposition of organic matter just like oil and coal. Unlike oil and coal, though, it can come from almost any organic matter, whereas coal comes only from plant matter and oil comes almost exclusively from plankton and microplankton remains. Natural gas can come from both of these sources as well. This is why you often find it associated with both oil wells and coal mines. Natural gas can also come from unconventional sources as well. It is produced by dead plant matter decay in swamps and rice fields. Animals such as cattle and termites produce large quantities as a byproduct of digestion. These sources, though, cannot be tapped for energy use. Other unconventional sources such as landfills, manure digesters and wastewater treatment plants are used to produce natural gas. It is a natural gas that is trapped within coal seams. The natural gas, mostly methane, got there during the coal creation process as some of the plant matter was broken down by pressure, heat and bacteria. Unlike some deposits of natural gas in Colorado and Wyoming, this methane did not migrate from the coal seam to become lodged in sedimentary rocks nearby. Due to the large amount of surface area inside the coal that can trap the gas, the coal seam can store up to 6 or 7 times what a conventional rock formation will hold. This means that these formations could produce vast quantities of natural gas. Besides the potential increase in reserves, coal bed methane has a few other characteristics that make it desirable. Natural gas that is associated with petroleum reserves is usually found at depths that are about 1 to 4 miles deep within the earth. This means that drilling to get these reserves is very costly. Furthermore, the pressures found at these depths means that pore spaces within the rocks is usually very tight, causing low permeability in the rock and harming production. Coal bed methane, on the other hand, is usually found at very shallow depths of anywhere from a couple of 100 feet to maybe a mile. This greatly reduces the price of drilling. The lower pressure at these depths means that natural gas can more readily flow from the coal, which increases production and further reduces cost. Coal bed methane does have some problems, especially when one considers the effect on the environment. Currently, our knowledge of extraction of natural gas from coal beds is still in its infancy. We do not understand how best to produce natural gas from these areas, nor do we know what environmental damage will be done by doing so. Much more research is needed to properly understand the particulars of this situation. Unfortunately, there are many forces that are pushing the extraction from coal beds right now, which could cause huge problems in the near future. Another potentially large source of natural gas is methane hydrate formations. These are solid crystalline features that are composed of a combination of methane, water ice and other gases. The methane and gases are trapped in the lattice structure of the water ice, which like coal beds can hold much more natural gas than normal rock features. These hydrate formations are usually found on the ocean floor where there is high pressure and near freezing temperatures. This usually requires water depths greater than 300 feet. Knowledge about these structures is quite slim. For one thing, we are not sure how they form. It could be that the methane is produced by bacteria near the seafloor that are decomposing organic sediments. However, it might also be that the methane originates from oil deposits deep within the earth that leaks to the seafloor bottom through faults and cracks. Either way, it is still unknown how the methane gets trapped within an ice lattice. The lack of this knowledge means that we have no idea what conditions would be favorable for their formation. This limits our ability to search for such structures. Another matter that is unknown about methane hydrates is their stability. The ice lattice structure is fairly delicate, being much more fragile than a sedimentary rock would be that contains natural gas. If the hydrates should break down, it would cause a massive release of methane into the atmosphere. By some estimates, there is 3,000 times the amount of methane in hydrate formations that is found in the atmosphere currently. Lastly, we have no idea how much methane hydrate there is in the world. The USGS estimates that there is twice the amount of carbon to be found in methane hydrate deposits as there is in all other fossil fuels combined. However, this estimate is made with scant information and could very well be wild speculation. There is better data for the existence of methane hydrates in certain locations. While the potential for methane hydrates as an energy source are quite high, our current lack of knowledge about their properties limits our ability to pursue.